Howdy, this time we're going to look at geometric sequences, but I'm just going to do examples this time, alright? Now I've done the notes on the page up above, so it might refer us to some of those, and so we'll look at them when we get there. So the first one says, find the 100th term of the first sequence above. So we're going to go up to the first sequence. There it is. UN equals 2 times 5 to the n minus 1. That was because there was a constant or common ratio of 5 every single time you multiplied by 5 to get to the next step. Alright, so UN equals 2 times 5 to the n minus 1. So U100 equals 2 times 5 to the n, which is 100, minus 1. Okay, and that's correct. Double check. 2 times 5 to the n minus 1. Yes, it is. And so now we can just plug that straight into our calculator. 2 times, now I can tell you right now, it's not going to like it, because 5 to the 99th is not a nice number. It's huge. So, okay, well, it'll give us a number, but you're not really going to be able to get much out of that, because you're only going to see a few of the digits. And this number is times 10 to the 69th. So let's just go 3.16 times 10 to the 69th. That's what the little e means on your calculator. Times 10 to the 69th power. Okay, so there you go. It's a big number. But what do you expect? You just multiplied by 5 99 times. All right? So here we go. Now we'll look at the next one. 3 consecutive terms in a geometric sequence are k minus 1, 2k, and 21 minus k. Now we've got the equations up above. We have the one that gives us the general term, and we also have the one that tells us about the constant ratio. Now again, we don't know if this is the first term or the last term or the middle term, nor do we know anything about them particularly. We don't know the constant ratio at this point. So what we will do is we do know that there will be a constant ratio. The constant ratio or common ratio will always be the second number over the first. So let's go 2k over k minus 1 equals r, but also 21 minus k over 2k equals r, because you should get the same ratio every time. Every second one divided by the one right before it should give you the same ratio if it is geometric, which it is. So now we can just set those two things equal to each other. 2k over k minus 1 equals 21 minus k over 2k. And so now we can cross multiply. 2k times 2k is 4k squared. We can do this as well. So k times, this will be a FOIL, k minus 1 times 21 minus k. So that will give me a negative k squared. It will give me a plus k and a plus 21k, so plus 22k. And then I've got negative 1 times 21, which would be minus 21. So at this point, I'm going to move everything over to the left-hand side, which is going to give me 5k squared minus 22k plus 21 equals 0. So I added k squared, I subtracted 22k, and I added 21. And so at this point, we want to factor, if we can, and hopefully we can. So there we go. Okay, and then we've got 21. Oh, sorry, that's one of those has got to be a 5k, huh? So 5k and k, and the signs will both have to be subtraction. And then let's go with 3 and 7, because 5 times negative 3 is negative 15, and negative 7 times k is negative 7. Negative 15 and negative 7 just happen to add up together to give me negative 22. So at this point, we can solve for each of those. So k could equal 3, because k minus 3 could be 0, or k could equal 7 over 5. And those are both okay. They should both work out. And if you want to check, you can go ahead and plug those back in and check out the ratio, and it should work out for you. Wonderful. 2 answers. How about that? Okay. So now let's go for letter 3. If you 3, the third term is 8, and u8 is negative 17 for a geometric sequence, find un. Okay, so what we're going to do, I think I did the wrong numbers here. Yeah, I wrote down the wrong numbers. Man, Mr. Bauwater, you're so smart. You put down the wrong numbers. Okay, well, you know, I guess we're just going to skip that one. Sorry. I'll have to try to figure out what question that was supposed to be. So, give me just a second. Okay, I done fixed it. I'm sorry. I just copied the problem from the arithmetic sequences, so it's fixed now. If u2 equals negative 6 and u5 equals 162 for a geometric sequence, find un. The other numbers, you could have done it, but I tell you, it's not going to be pretty, and I don't want to take time with something that ain't going to be pretty. So, here we go. Let's do u2 equals negative 6 and u5 is 162. Now, there's a couple of ways you can do this. You can do it similar to how we did the arithmetic sequences. You can just kind of reason through it, right? So you could say, well, to get from u2 to u3 to u4 to u5, that means I'm going to have to multiply or divide by the same thing, multiply 3 different times. So I'm going to take 162 and divide by negative 6. 162 divided by negative 6. And I'm going to get negative 27. And so negative 27 is what has to happen when I multiply by something, and then multiply that again, and multiply by that again. So something, some ratio to the third power should give me negative 27. So to solve for that, I would just take the, not the square root, but the cube root, because that's how I'm going to get rid of the cube. Now, this wouldn't work if it was anything more than a square root or cube. Well, it would work, but it's a little bit difficult for us to come up with quartic roots and quintic roots and that kind of stuff. So this method only works in some situations to find r equals negative 3. Okay, another method that would do just the same thing, and if you wanted to use a calculator, you could use a calculator for that, is that you can actually set up a couple of equations, right? We know that u2, is equal to the first term times r to the n minus 1. And you can do that for 5 as well. So u1 to the r times to the 5 minus 1. Now we know what u2 is. u2 is negative 6. And so that would be negative 6 equals u1 r to the first, and 162 equals u1 r to the fourth. Now at that point you can set the two u's, you have u1, and so you can solve for one of those u1s and you can substitute, or you can plug it into an equation, right? And so, or you could just say, well, since this is equal to negative 6 and u1r1, you could set up an equation that looks like this. 162 divided by negative 6 equals u1r to the fourth over u1r1, right? Because those two things are equal. So you can divide one side by one and one side by the other, and it should come out to be the same. The u's would cancel out. 162 divided by negative 6 is negative 27. And then subtract so that it would be, sorry, not u, but r to the third power. And so from that point, you would still have to take the cube root. Now, if you don't know how to do that, you can always use your calculator and just say negative 27 to the 1/3 power. Remember, the cube root is the same thing as the 1/3 power, which will give us the same number, negative 3. And so we get that r is negative 3. And so now we have our equation for un, which is equal to the first term, which we're going to have to find. So I was having to multiply by negative 3 each time. So you can either plug it in and solve for it. You now could put negative 3 in for one of these, or you can reason and just say, okay, well, u2 was negative 6, this was 18, and so on and so forth, which means that this is going to have to be 2, because I'm going to divide by negative 3 to get there. So un equals 2 times negative 3 to the n minus 1 power. There you go. That wasn't so bad. Now the last one, find the first term in number 3 that will exceed 1 million. Okay, well now that we have a general term, we can find out where we're going to get that term that's 1 million. So we'll just put in 1 million for that. So we'll go 1 million equals 2 times negative 3 to the n minus 1. And so at this point, all you have to do is solve for n. And yes, that is going to require using a log, because we're going to have to find out which term n is. Now, it might be a decimal. If it is, then we just go, you have to round up, because it has to be exceeding 1 million. So let's go ahead, we'll divide by 2, which is going to give us 500,000 is equal to negative 3 to the n minus 1 power. And so now we should be able to go ahead and do some math to solve for that. So at this point, we're going to have to do a little bit of a change, because you can't take the log of a negative base. And if we rewrote this as it was, it would be log base negative 3 of 500,000 is equal to n minus 1. And that would be a problem, because you can't have a negative base for a log. The other thing is, the only thing that the negative here is doing is that it's causing the numbers to alternate between positive and negative. And we know that if it's a negative number, it's not exceeding 1 million. So we can actually take this and adjust it for our purposes so that it's a positive 3. All right, because a positive 3 will still give us the correct number every time. It just won't give us the negative. All right, so we're going to go ahead and put that in, and then we'll check it later to make sure that it's giving us the number that we want. If not, then it'll have to be the next one. So we're going to go ahead and change it to a positive. We'll go log base 3 of 500,000 equals n minus 1. And then we'll add 1 to each side, and we'll do a little change of base here. Change of base says that log of 500,000 divided by the log of 3, we'll add the 1 to both sides, equals n. So let's go ahead and figure that out. So we'll go log of 500,000 divided by the log of 3. We'll add 1. So we get 12.9. So that means that the 13th term is going to have a value, an absolute value that's larger than 1 million. Now, if I put 13 here, 13 minus 1 is going to be 12, which is an even number, and an even power of a negative is going to give us a positive answer, and so that should work out. So let's go ahead and check it. Let's go un equals 2 times negative 3 to the 13 minus 1. So 2 times negative 3 to the 13 minus 1, which is 12, and we get 1,062,882. And there you go. That is the first term of this sequence that exceeds 1 million. And you know that's right, because if you go back one more term, you're going to have to divide by 3, which isn't going to be more than 1 million. All right? That's actually kind of neat that it only takes you 13 terms. It's the 13th term when you finally break 1 million. That's pretty fast. All right? Anyway, that's the problem. Hopefully it was helpful. Ciao.